So the goal of these chats is just to supplement the information that we have that you'll be quizzed on, as well as just to give you the opportunity to interact with real life scientists. So our guest today, we have a very special guest, uh, Dr. Sara Mazrouei. She's a planetary scientist and a science communicator who's passionate about sharing the wonders of the universe with the public. She earned her PhD from the University of Toronto and currently works on multiple educational outreach efforts. So please join me in welcoming Dr. Sara.
Hi, everyone. Hi, Adisa. Thanks for having me today.
No problem. Thank you for being here.
Are we ready to talk about space today? All right. Would you like me to start with a little bit of a background on, I guess, how I got interested in space?
Please.
Should we do that? Okay. So I'll start taking you through a little bit of a journey of how I became interested in space. And if I can just ask for the slides to be shared. So we'll try to share the screen so that you can see some slides. And I'll tell you a little bit about my background, how I became interested in space, what I've done, what my research has been about. One of my first memories is when I was about maybe 8, 9, 10, can't really tell, somewhere around that age. And I was walking home and I looked up at the sky and I saw something that I wouldn't see any other night. It wasn't the stars, it wasn't the moon, but it was something that had a really bright tail. And I didn't know what that was. I learned that that was called a comet. So it's not really a star. It's further away from our moon and some of the planets close to us. It has a really, really shiny, bright tail. We call those comets. That one in particular was Comet Hale-Bopp. And I remember asking people about it, and they kept saying, you know, that's sort of like a once in a lifetime opportunity to see a comet that bright. It's not common. We don't get to see them every night. So that concept of, you know, once in a lifetime, it's pretty unique, it's pretty special. That got me excited a little bit. And then on the next slide is another thing that I saw probably at the age of 12. Some of you, if you live in Toronto or around Toronto, you may have seen a partial solar eclipse a few years ago that we had right here in Toronto. I got to also see a total solar eclipse back when I was 12, 13. And I remember it was really weird in a way. The sky started to get dark in the middle of the day, and even birds started flying home, just like they do around sunset. And then, you know, and that's solar eclipse is usually when our Earth, the moon, and the sun align in such a way that the moon blocks the sun, so the light from the sun doesn't reach us anymore. And that was pretty exciting. Again, I was told, you know, this is a once in a lifetime thing. You don't get to see a solar eclipse all the time. Partial ones are more common than total ones. But still, that got me pretty excited, pretty interested. And if we go to the next slide, I started to follow my passion. I wanted to learn more about, well, how do solar eclipses form? How do comets form? Where do they come from? And I heard that in astronomy and space and planetary science, there's always so much unknown. So the more you research and the more you figure out stuff, there's still so much that we don't know about. And I'm like, that's cool. You know, in school when you're studying things and you keep reading, like, I don't know, Darwin's theory and whatever's theory. And I'm like, I want a theory named after me or something, you know, I want to discover something new. So I studied at York University. I did my bachelor's and master's there. I studied space science. And then I went on to do my PhD, and that's just a picture of me working at the observatory at York University. For my master's research, I started studying asteroids. You might ask what asteroids are. Some of you might already know what asteroids are. Some may not. On the next slide, I'm going to show you a great range of asteroids. So asteroids are not quite large enough to be like planets. And they have like odd shapes as well. Most of them are rocky. Some of them could be metallic, but they don't have an atmosphere. So we call them airless. and they could be anywhere from beyond our Earth all the way to Jupiter. And because Jupiter is so massive, it attracts a lot of them towards it. So a lot of them are between Mars and Jupiter. And they vary a lot in range. So Vesta, asteroid Vesta, is one of the largest asteroids that we know. And then if you look to the side, there's also a super, super tiny one right at the bottom. Its name is Itokawa. And that's the asteroid that I studied for my master's. I'm going to show you a close-up image on the next slide. Some say it looks like a potato. Others say it looks like a sea otter, right? Pretty sure it does look like a sea otter. So my job was to sit there and to count all the rocks that are on this asteroid, map all of them, and then try to figure out if the head of this sea otter was any different than its body. And if it was, from the rocks on it, then we could learn that, hey, maybe they were two different asteroids that came together at some point or another, or if the neck kind of got pushed in due to another collision at some point or another. So we can study rocks on the surface to try and figure out how these asteroids have formed and evolved. And the pictures that we get from these asteroids, we have spacecrafts that fly all the way from here. They take multiple years to get to an asteroid, and they orbit the asteroids, take a lot of pictures in different wavelengths. So this one is in a visible image. So just like you would go out and take a picture with your smartphone or a camera, except these spacecrafts are going around these asteroids, snapping photos, getting closer, and letting us know what they look like. And another reason why I studied this asteroid was because at the same time, Canada was trying to make an instrument to contribute to a new mission called OSIRIS-REx. And if we can go to the next slide, I helped with one of the preliminary parts of the OSIRIS-REx mission. I'm trying to understand what asteroids are made up of. I got to go to Cape Canaveral to watch the launch of this spacecraft, and it finally got to the asteroid about a while ago, a few months ago to a year ago. But the cool thing with asteroids is that before we go to them, we start using ground telescopes. So ground space telescopes, they could be optical or they could be radio telescopes, where we try to image an asteroid or get some information about it. Now with asteroid Bennu, which is the asteroid that OSIRIS-REx has gone to, all we know about it was that it was round-ish. That's it. That's all we knew. And we knew that it could maybe, in a few thousand years, maybe collide with the Earth, maybe not. So we wanted to learn more about it. So we're like, all right, let's build a spacecraft. Let's put all of these instruments on it and go do some science. And Canada built the LiDAR instrument, which kind of works like a laser. They keep shooting laser beams at the asteroid, and they measure how long it takes for that light to get back to us. So imagine if we were bouncing some light off of the wall and how long it would take to come back to us. If something is further away from us, it would take longer for the light to come back. So that could tell us if there were any deep areas on the asteroid, if there were any tall areas like a mountain or not. And now, with the help of OSIRIS-REx, I'm going to try to show you a video maybe for a few seconds. We've been able to get so much more details about this asteroid. And whenever a spacecraft gets to an asteroid, the first thing it does is it has to survey it for a little bit. So we're going to go around a little bit, try to do some pictures from afar, try to see if we can figure out its shape, what it really looks like. And what this mission wants to do is bring some samples back to Earth. But it can't just land anywhere or grab samples from anywhere. We have to do a good survey, make sure that we can actually get a sample from a good place. So it did some survey missions, and just yesterday, it had to do a rehearsal. So if you've ever done a dance performance or a theater performance, you always do a rehearsal. You don't just jump on stage and do your big play in front of everybody, right? You have to do a practice run first. And that's what OSIRIS-REx was doing yesterday. It was making sure that its arm that's supposed to give a high five to the asteroid to collect some samples was opening up properly. and making sure that the sites it wants to get samples for are good, that the scientists actually like those spots and were able to get some samples. And then there came the moon. So for my PhD work, after I was done studying asteroids, I said, okay, now I want to come back a little bit closer to the Earth, and I want to learn more about our own moon. It's so close to us, but it's very special. Our moon doesn't have an atmosphere. It doesn't have any snow. It doesn't have any rain. So no weathering, no tectonic activity. So whatever that happens on the moon, it stays there. So in a sense, it's like a time capsule because the Earth and the moon are so close to each other. Anything that would have happened to the moon would have happened to the Earth as well. But we've got a lot of snow, just leave something out for a few days here and the wind is going to blow it, and there's going to be snow, and there's going to be sunshine, and there's going to be rain, and it's going to get rid of all of that. But on the moon, there's a lot that we can study. And I decided to study craters on the moon, which are those circular features we can see. So when asteroids or other space rocks hit the surface of the moon, they create these holes that we call craters. And trying to understand craters can tell us more about when those events happened, and therefore a little bit about the history of the moon and the Earth. And I wanted to share a special crater with you. One of my favorite craters on the next slide is called Tycho crater. And the other one on the side, that's my dog Tycho. Because I was studying craters a lot during my PhD, I decided to also name my dog Tycho. So yeah, there's a little fun fact about that. And another cool thing that I got to do throughout my PhD work was to do an internship. So I'll show you on the next slide. I got to work with a group of scientists and engineers from all around the world to work for future moon missions. So with the talks of having humans go back to the moon, we have to figure out what are the best spots to go back onto the moon. What are some samples that we want to bring back? And we have so many cool images right now. We have the Lunar Reconnaissance Orbiter. That's a spacecraft going around the moon. It's taking a lot of different images. So from the near side, which is the side of the moon that we see, and from the far side, we get a lot of images. We learn a lot more about it. We can see down to meter-sized rocks on the surface of the moon with this spacecraft. And with the team, we got to decide what are some of the best spots for astronauts to land, and which path could they take to then go on to the next spot, and what type of rocks they should bring back. And that was also a lot of fun. So with that, I just wanted to tell you a little bit about my own research, what I've done, and what a space scientist or planetary scientist could probably study and research. Now, would you like me to, should we try to answer some questions from the audience?
Perfect. That sounds like a very good plan. Thank you very much for that presentation. That was really, really, really interesting. So some questions from the audience that was sent in previously. So one really stands out here. The first question is space real?
Space is real. Well, what is your definition of space? I think we call space anything. I mean, all of us are in space. Even the Earth is in space. So it's part of our solar system, part of our 8 planets. And then we are all part of the Milky Way galaxy, and the galaxy is part of, a bunch of other galaxies. So yes, space is very real, and we've got a lot of spacecraft that are taking a ton of pictures from different planets, galaxies, star systems. So now we have a lot of evidence for them as well.
Okay, perfect. The next question is, do light and sound travel faster or slower in space?
That's a really good question. So in space, we say that space, there's vacuum in space, meaning that there's no atmosphere, there's nothing really there. And the speed of light is constant in a vacuum. It's just going around. It just travels at a constant speed. Really same with sound, except sound can't travel in vacuum. You do need some medium for it to go through. And if we think about it in terms of on Earth, sound can travel at different speeds. So it could go faster in liquid than in air, for example. And that's why whales can communicate like over a longer distance with one another in the water than humans can. Like if I shout, maybe my neighbors across can hear me, but not on the other side of Toronto.
Okay, so we have some live questions right now popping up in the chat. First question is, have black holes been proven to exist?
Yeah, that's a really good question. And just last year, actually, we were able to get the first image of a black hole as well. So we've always known that they existed, because if we look at any galaxies, there's always a black void in the middle, which means that light cannot escape from it. So it always looks dark and it looks black. But just last year, we were actually able to get the first image of a black hole as well, which was really exciting. If you Google the first image of a black hole, you'll get that as well. And the neat thing about it is that it took scientists from across the world using different telescopes to sort of combine the data and to create that photograph. So it was pretty neat.
So collaboration is very important.
It is very important, yeah.
So the second question here is, how big was the asteroid that you studied?
Oh, Itokawa was pretty small. I think if I remember correctly, it could have been about a few kilometers across. So yeah, because I remember I made a photograph of it next to the CN Tower as well. So I would say a few kilometers and like the length of asteroid Itokawa.
Okay, so not too big.
Not too big. That asteroid was really, really small. Yeah.
Okay, perfect. We have another question here. Oh, this is an interesting one. Questions about the Big Bang. This question is asking, is there proof that the Big Bang happened?
There's still no, I guess, proof in terms of having a photograph or video, but we do have spacecrafts that are studying cosmic microwave backgrounds, which are the remnants of the energy that was left over from the Big Bang. So our eyes can only see visible light. But if we go through the light spectrum, if we go through different wavelengths of it, for example, microwave wavelength, we can see things that our eyes would not be able to see. So we do have some images that give us very good reassuring signs of events that would have happened right after the Big Bang.
Okay, perfect. Oh, this one is interesting. What is a black hole made of?
Oh, that's a really good question. So a black hole, usually at the center of it has a neutrino star. So usually when stars go through their cycles, so one of them, if it goes supernova and then it collapses within its core, the very tiny core of old stars would have been what a black hole is made up of. But they're so dense, they're so heavy that they attract all the light and do not allow any light to escape.
Okay. And so on that concept of it attracting all the light, this question is, if light is not able to escape a black hole, how was the picture taken?
That's a really good question. And if you look at it, you still see the black hole, but you have all the light around it. So the picture, it's still showing you literally a black circle, but what tells you that it's a black hole, it's all the light that's around it. So from a certain distance from the center of a black hole, light is able to still exist. But once it steps over, it sort of falls into the black hole gravity and can no longer escape. So we still see the black hole, but around it is all the light that still exists and cannot be trapped within the black hole.
Okay, nice. Okay, so let's take a little step into what we all see here in our favorite science fiction movies. So now we're going to talk about aliens. Is that okay?
Okay, yeah.
All right.
Let's do it.
A few people are asking about the aliens on Mars. What is there proof of any extraterrestrial life? Like how would we study this? What are we looking for when we look for extraterrestrial life?
Yeah, so extraterrestrial life has, I guess, different meanings. But with all the hype about going to Mars and looking for life, we're not necessarily looking for life in the form that you and I are in, but we're looking for any evidence, so any microbial or, any small amount of, single cell life that could exist. We're not necessarily looking for intelligent life. But with Mars, for example, for years now, we've been sending spacecrafts either to orbit or to land and to rove around and give us as much information as we can. And slowly we're building our understanding of Mars and getting more clues. It's sort of like trying to solve a puzzle. So originally, the first images of Mars showed these channels that humans at first thought they were human-made. But with the first set of spacecraft, we realized that no, they were naturally forming channels just like we have here on Earth. And then we started sending landers that then discovered, oh, these are signs that water existed here on the surface of Mars at some point or another. So right now we know that on Mars, water did exist for sure at some point, in liquid form as well. And then our next thing is, well, if there was water, there was probably some sort of life as well. And now we're looking for those organic material. We're trying to look for those signs. And with the amount of information we have now, we know that there's a lot of spots that would have had water, and we're sending the next set of spacecrafts there. Actually, this year, the summer of 2020, July of 2020, is where we have one of the windows of sending this next set of Mars spacecrafts to Mars. That window happens about every 2 years or so, which gives us the shortest time to get to Mars, about 6 months. So this July, we've got at least, I think we have 4 in plans to send, 4 spacecraft and rovers to send to Mars if they don't get delayed. So that would be really exciting to see.
That would be pretty cool.
Yeah.
So we have about 5 more minutes here, so I'll ask you just 2 more questions. Is that okay?
Sure, yeah.
Okay, so I have a question here about gravity. So the question says, can gravity form waves? And the second part of the question says, does the influence of gravity extend out forever?
Gravity could have, so we've learned about gravitational waves. We thought that they could bend, so we had Einstein's theory, which I think are maybe they're referring to, and that was another big discovery of a few years ago, that Einstein had always had this theory that gravity could bend, and we got some evidence for it actually from some telescopes a few years ago. In terms of can gravity extend forever, that depends on the size of the object. So it wouldn't be infinite. It would depend on the size and the mass of the object. So a smaller object or a less dense object, for example, would have less gravity. You and I have gravity, but if, I still have to pick up my coffee mug. It's not going to get stuck to my hand because I don't have enough mass to sort of keep my coffee mug to my hand. But the Earth's gravity is a lot more than that. The sun's gravity is a lot more than the Earth. That's why the Earth is going around. So everything has gravity, and everything is always pulling on one another. But every object's gravity can only go as far as its mass would allow for it.
Ooh, very interesting. So the bigger the object, the greater the effect that its gravity can have on other objects.
The more massive, yeah. So it depends on how much mass and how dense it is, because we could have something that's fluffy and large, but something that's small and dense, right?
Perfect. Let me see if I can find one more nice question. This one here is about gamma rays. So the question is, how commonly do gamma ray bursts occur?
Gamma ray bursts. So that question I would have to Google to really answer you, because as a planetary scientist, I usually study things that are a lot closer to us and on the surface of objects, but gamma ray bursts, how? Okay, while you ask the next question, I'm going to see if Google can help me answer that question.
Let me see if I can find one more nice question here. This question is asking about the magnetic forces from planets, so like magnetic fields from planets. So it says, do all planets have a magnetic force? Like they, yeah.
Right. So all planets have a gravitational force, but
Mhm.
not all of, they don't all have a magnetic force. Whether they have a magnetic force or not depends on what they're made up of and what their cores are really made up of. But those that do have a magnetic field, they also produce auroras, or like as we call them, northern lights as well.
Mhm.
So you can see northern lights from some other planets as well, which are really, really cool and interesting. But no, not all planets have magnetic fields.
Okay.
And gamma ray bursts, Google is telling me that they could happen anywhere from every 10,000 years to one every million years.
Okay.
But that's just Google for now.
Right. So we're just out of time here. So one final question. No, you have to go. So this one is about everyone's favorite dwarf planet, Pluto. Why did it become a dwarf planet?
I know, we're all sad about Pluto. Well, as we start discovering more and more objects, we found more things in the solar system, like Vesta, for example, that I just showed you as an asteroid. It's big, it's round. Do we call that a planet as well or not? So we started discovering things that looked just like planets. So either we would have to keep growing our list of planets or start having a new definition for what a planet is. And the International Astronomical Union came up with a new definition for what a planet is. One, it has to be large enough to turn itself into a sphere, so have enough mass to turn itself into a sphere, which Pluto does have. Two is that it should be orbiting the sun, which Pluto does as well, so it does a full orbit around the sun. But the third one, which disqualified Pluto as a planet, is that it has to be the primary object around its path over the sun. So it has to clear its orbit around the sun. Unfortunately, Pluto cuts into Neptune's path around the sun. And that's why Pluto is no longer a planet, but it's still there, right?
It still exists. All right, perfect. So I would just like to thank you for taking the time for doing this with us. It was very, very informative. I definitely learned a lot. And I hope everyone in the audience can say, I'm pretty sure everyone can say the same. Audience member here says thank you very much.
Oh, thank you. I see another question I'll answer super quickly, if
Okay,
you don't
for sure.
mind, about
Yeah.
Betelgeuse. Betelgeuse has been super exciting. For those of you that don't know about Betelgeuse, it's this red star that you are able to see in the night sky right now. It could go supernova at any point, like it's towards the end of its life cycle. But it could happen anytime from today until another 10,000 years. The reason that it was, we saw it at the dimmest that we had seen ever, I guess, and now it's starting to get back to its regular brightness. It's because it's a variable star. So it does change its brightness throughout the time of the year. So it could go dim and it could become bright. So it's totally normal. Nothing special about Betelgeuse yet. It's still up there existing.
Okay. Right. All right. Now I didn't know. I have to go Google that one. I didn't know anything about that. Now I have something to study up on myself.
And it's a nice constellation to find too. It's in the Orion constellation. Super easy to find once you've Googled it once.
Okay, perfect. All right. And with that, we wrap up our first scientist chat. Thank you very much for joining us today, Sarah. Thank you, everyone in the audience, for joining us. And please look out for our newsletters to come out soon about the following scientist chat sessions. Do you have any final parting words, Sarah?
No, keep looking up, keep asking a lot of good questions, and space rocks.
All right. All right. Thank you.
Bye.
Bye.